Hello, my name is John Coffey, and I am currently an undergraduate researcher within the Impulse Manufacturing Laboratory. This video gives a short description of the Openable Electromagnetic Actuator. First, however, let's start off with an overview of electromagnetic forming. Electromagnetic forming is a process that utilizes a solenoid coil, a capacitor bank, and a workpiece. The workpiece is placed around the coil, as shown in the picture here, and the coil is attached to the capacitor bank. The following short clip is of an electromagnetic ring expansion. Energy is gathered within the bank and is then released. This current flows through the coil, thereby inducing a current within the conductive workpiece. Due to the opposing nature of the currents, the magnetic fields created are also opposing. Due to the resulting repulsive force between the ring and the coil, the ring expands. Within this short animation, the red arrows are symbolizing the current that is set through the actuator assembly, and the green arrows are symbolizing the induced current within the workpiece. This process is the same with a tubular workpiece, even though a ring expansion is shown. This process is capable of a few different operations, such as expansion and compression, as well as the propulsion of a flat workpiece towards a die where the workpiece can be formed, sheared, embossed, or welded. One of the neat applications of this technology is in the forming of semi-finished pieces, due to the lack of direct contact between the workpiece and the actuator. This particular openable actuator is used for compression. A piece of hexagonal 1018 steel rod is placed within the 6061 T6 annealed aluminum tube after being cleaned. The aluminum tube was annealed at 525 degrees Celsius for about an hour. A piece of tape is then wrapped around to the end of the steel so that the steel is centered within the aluminum tube. The tube is formed beneath the tape so that the inner layer does not affect the results. There could be better ways of positioning the tube and the rod concentrically, but for the sake of this demonstration, we use tape. The workpiece is placed within the assembly and is secured with 3 C-clamps that are insulated from the aluminum enclosure using pieces of G10. The charge is then released through the coil. The openable actuator utilizes tertiarily induced currents to form the workpiece. The coil induces a current within the aluminum enclosure, then, due to the currents within the aluminum enclosure, a current is induced within the aluminum tube. Due to the compressive forces on it, the aluminum tube then crimps onto the steel rod. Fire in the hole! As you can see, the voltage, the blue line, and the current, the green line, are traced while the experiment is being performed. They are shown on the monitor to the left. This allows us to see the time that it took the part to be formed, as well as giving us some information about the individual experiment so that calculations can be performed. This was done at 3 different energy levels. As we see here, the conformance decreases with the decrease in energy level from 8 kilojoules to 4 kilojoules. Unfortunately, the tertiary currents are incredibly diminished in comparison to those released by the capacitor bank. We ran a comparative test using non-annealed T6 aluminum tube at 6 kilojoules with a disposable electromagnetic actuator. A disposable coil within the disposable electromagnetic actuator uses the primary current to induce currents within the workpiece. This leads to greater overall efficiency. However, the coil that was used is destroyed in the process. This is the conformal joint that was formed using the T6 aluminum tube that was not annealed. The joint formed is comparable to the 8 kilojoule joint in the O actuator. However, the disposable coil shows weld-like deformation at the end of the aluminum tube, whereas the 8 kilojoule one does not. Even though the O actuator is relatively inefficient, no waste is formed in the process, so this would be ideal for clean room processes. If you would like to learn more about O actuators or the Impulse Manufacturing Lab, please check out our webpage, which is a link in the description, and subscribe. Thanks for watching!